Welcome everybody to the 33rd episode of the Struggling Scientist podcast. This is a podcast by scientists, for scientists, anybody science adjacent, and perhaps even hobbyist. My name is Susanne and I'm here with my co-host, Jerome.
Hi.
Today we have another episode with Dave, Dr. Dave Speijer, and it's a surprise episode. Not so much for our listeners, but definitely for us, because we don't know exactly what we're going to talk about. So let's start. So Dave, why don't you tell us what is this episode going to be about?
Now, first I wanted to say that this, of course, was due to popular demand, but then I would start with a lie. I just pressured Jaron to allow me to talk about one of my favorite subjects, and that's eukaryogenesis. So, where do eukaryotes come from? And now, there are people that have theories that this already started out at the beginning of life together with the prokaryotes. So these are archaeons and bacteria. But most people now know that it's a rather recent development compared to prokaryotes that were around from 3.8 billion years ago. But if I say recent, you still have to say 1.8 billion years ago. So recent, relatively speaking, you could say. But it took 2 billion years, according to most people, before eukaryotes evolved. And there are two main theories, you could say. The Archezoan, the older theory, that says, okay, you have an archeon, and that became complex, more and more complex, started to have internal membranes and a nucleus, etc. And really a pre-eukaryote, you could say. And that pre-eukaryote evolved the capacity to phagocytose. And lo and behold, what did it phagocytose? Well, an alpha proteobacterium, and that's the mitochondrion. And
yes.
Oh, presto!
This I've definitely heard about.
Yes. Okay, so there we have the eukaryote. Okay, and that evolved into LECA, the last eukaryotic common ancestor, and all present-day eukaryotes, whether these are trypanosomes or malaria parasites or plants or algae or animals such as us, came from that one. And I don't agree. I don't think it happened that way, because there's an alternative, and that alternative is the symbiogenic theory. And a symbiogenic theory says, okay, from symbiosis, certain things appeared. So symbiogenic. It's due to the fact that an archeon and an alpha proteobacterium had to live together that all the eukaryotic characteristics, or most of the eukaryotic characteristics, can be understood. And why do I like that theory so much better? First of all, because I stumbled into it with one of my own theories. You have to be honest. And I have to say, yeah, I came up with a theory, and that was a symbiogenic theory for one eukaryotic characteristic, and that's the peroxisome. So peroxisomes, every eukaryote has a peroxisome, and the few that don't have also lost mitochondria, so they don't count.
Okay.
Don't you agree? Hey, a eukaryote without a mitochondrion, that's not a real eukaryote. Come on.
Okay.
And it's a derived state, you could say. So the peroxisomes, I think you can understand from symbiogenic perspective. So that's why I got interested in these kind of theories. And now, of course, I have to invent all kinds of reasonings why a symbiogenic theory is superior to the old archeozoan model. So let's start and demolish the archeozoan theory. You already start laughing at, let's demolish something. Yeah, that would be great. So how do you do that? Well, first of all, the examples of archeozoans, people said, but this is the pre-eukaryote without a mitochondrion, but for the rest, these are all derived states. We now analyze them, and we know from their genomes, they had mitochondria, but lost them. So these are not the real ancestors. No, they're derived states that look like ancestors. And this kind of confusion I always refer to as CAF. That means the contemporary ancestor fallacy. So you see something round, it looks like the kind of intermediate you expect, and then straight away, that must be it. But of course, you're looking at things from a rather strange vantage point, because we're now 3.8 billion years further in evolution, and also these intermediates evolved.
Mm-hmm.
So these are derived states and not the real ancestors. And secondly, there's something strange with this idea that you begin with an archaeon and it becomes more and more complex on its own. And that's a very old kind of prejudice. We all think, yeah, evolution goes into the direction of more and more complexity. But why? Why would that happen? Bacteria and archaea are still around and they're doing fine, believe me. After we have disappeared, archaea and bacteria will still be going here on for a very long time. So there's no intrinsic tendency towards greater complexity. But it still happens. We see very complex organisms. But that you should explain due to evolutionary pressures all the time evolving. Now, there's no intrinsic pressure for an archaeon to think, well, it's a good idea. I need an internal membrane or I need a nucleus or something. There should be a driving force. There should be advantages.
Mm-hmm.
And if you look at archaea and bacteria, you hardly ever you see some kind of internal membranes, but never something that comes close to a eukaryote. So what could be evolutionary pressures that allow from a symbiosis of an archaeon and a bacterium, slowly but steadily, the evolution of a real eukaryote? So you must find these kind of evolutionary forces from the symbiosis. That's what I think. Then you have more tiny steps, and that's the way evolution works. Still, the outcome can be gigantically different because a eukaryote is really, really different from an archaeon or an alpha proteobacterium. Mm-hmm. But the steps, the intermediate steps, can't be too big. And there's no intrinsic tendency for the host, as it is called, the archaeon, to become more and more complex. So let me now, because you don't look convinced, Suzanne, and I...
Well, I was wondering, why do you think you don't see those intermediates then?
Okay, that's a very good point. I think that during that kind of evolution, maybe we're really lucky and we will find some kind of intermediate, but I think that all the intermediates haven't stood a chance to make their living after they were followed by a more complicated one that was much more efficient. So you don't see these kind of intermediates anymore. And I think that actually the process went rather rapid as well, because I'm now going to try to convince you about what kind of evolutionary forces led to a lot of eukaryotic adaptations and real eukaryotic traits. And afterwards you can say, no, I don't believe it, but then we'll have a nice discussion.
And when you say rapid, do you mean 100,000 years?
Well, I don't know exactly, but for evolution, on evolutionary terms, I don't think this will be 10 or 20 million years. You have to remember that these are still prokaryotes. And the prokaryote lifetime, the doubling time of a prokaryote isn't comparable to what we see with animals, for instance. So that you also have to take into account. So let's say 1 million years or something. In evolutionary terms, that's really a rapid process. Okay, but here I'm speculating. But now let's speculate about the evolutionary driving forces. That would be nice. Okay, so I think you start out with an archaeon and you start out with a bacterium. They had a pre-symbiosis. Now, a symbiosis is always exchange of something. Something that one of them can't use and the other one can, and the other way around. Now, I think the exchange actually, but now I'm getting into details. Let me first, where does the theory of symbiogenesis really start? That's with the so-called hydrogen hypothesis in 1998 by Müller and Martin. Now, I don't believe that their specific model is correct. I don't think it was hydrogen exchange. This is the exchange I talked about. But this was the really the first example of a real symbiogenic theory in nature. So he started out with an archaeon and a bacterium, and he says, okay, if they have to live together, then slowly but steadily they evolve the things that we now see in eukaryotes. And that's a major breakthrough. That's a paradigm shift. But I just don't believe his specific example, because he was influenced by the eukaryotes nowadays that have hydrogenosomes. You see, I don't like to pronounce things that are not normal in the world of mitochondria. But these are also derived states, according to me, due to horizontal gene transfer. They aren't old. So he was misled, I think, in that respect. So what's the exchange I think that occurred? It's the exchange that we still see in eukaryotes. Now, you know your basic metabolism. So what goes into the mitochondria, for instance? Well, things like pyruvate. And then pyruvate is further metabolized in mitochondria and completely oxidized. And sometimes other things go out to the cytoplasm again. Not ATP, ADP. Yeah? That's somewhat more weird, and that's later. So probably, and that's my favorite model, you had an archaeon and a bacterium living in an environment with fluctuating oxygen. And the archaeon couldn't use oxygen, but the alpha proteobacterium had a complete respiratory chain and could. Now, when there was oxygen, all good, everything goes into the alpha proteobacterium that secretes something for the archaeon. And where there's no oxygen, then it's the other way around. So that's the basic idea of what was the pre-symbiosis. Now, then, because that kind of symbiosis becomes more and more intense, and there are archaea, I should mention, of the Asgard film, that can have large extensions. And most people, me and a few other people think that these large extensions are there to make exchange of metabolites much more easy. And then you can imagine, hey, if these become longer, then things can become engulfed, etc., etc. And due to a kind of accident, these alpha proteobacteria end up on the inside of the host. So now you finally have the merger of the two prokaryotes at the beginning of the eukaryotic clade. So far, so good. Do you still think, well, this could have happened? Or are you already very critical? Come on.
No, I can still see it.
Okay, so
I actually have a question about derived states. What do you think led to just the derived states? Just by chance that it happened, or
no? Actually, it's interesting that because eukaryotes were so enormously successful, you get structured environments of eukaryotes. So some of these derived states, for instance, happen in parasites where eukaryotes parasitize other eukaryotes. And in the gut, there's no oxygen, but there can be, for instance, hydrogen. There are many states that are derived because now nature becomes much more complicated with the evolution of the eukaryote. So these kind of situations. And we know that a lot of eukaryotic organisms become really simple again. Some parasites have practically lost everything. But you know that they evolved from Leica, which was a pretty complicated organism. So that's what I mean in that case. Yep. Okay, so now for our main event. What about the driving forces that led to all these kind of eukaryotic adaptations? And here, most people say that I go completely overboard because I reduce practically everything to one driving force. And Jaron has the unpleasant experience to being locked up in a room with me. So he knows that I'm now going to talk about reactive oxygen species.
Yes.
Ta-da! Of course. Yes. I'm going to do that. So what happens? You have an organism, an alpha proteobacterium-like organism that uses oxygen as the final acceptor. On the plus side, you could say it can oxidize practically everything. It has beta oxidation. It can use fatty acids. It can break down amino acids, glucose, practically everything. And in a very efficient way. Because if you use oxygen, you really get shitloads of ATP. Sorry to the listeners, but shitloads really...
The technical term.
That's the technical term here, I agree. So you get an enormous amount of ATP, but of course there's a drawback. Oxygen is a double-edged sword, you could say. On the one hand, it's great. On the other hand,
kills you slowly.
Precisely, in the respiratory chain, electrons can be picked up prematurely by oxygen, and you get superoxide radicals, and you get hydroxyl radicals, and hydrogen peroxide. Ugh. And these can destroy practically everything. And I think that a lot of the things that we see with all eukaryotes are adaptations when you take ROS formation into account. Now, there are two things you can do with ROS. You can either try to suppress them, so come up with ways to have less ROS formation, or you can say, hey, yeah, but there's no getting around it. Let's adapt to such a certain extent that you can repair, that there are possibilities to live with oxygen. And I think a lot of the eukaryotic adaptations can be seen as either falling in category 1, suppressing ROS formation, or category 2, getting around the damage and living with ROS. So I'm going to start with the one that brought me into the symbiogenic camp, you could say, and that's my idea about peroxisomes. Now, okay. So why do I think you can explain peroxisomes when you take internal ROS formation into account? If you look at the way the respiratory chain is formed, then electrons come in either via complex 1 from NADH, or from complexes, you could say, after complex 1, like complex 2, succinate dehydrogenase, which uses FAD or FADH2 as a cofactor. By the way, the one that catalyzes the first step of beta oxidation, so the breakdown of fatty acid, also uses an FADH2 cofactor. So the dehydrogenase involved in that one gives off its electrons to the respiratory chain via an FAD cofactor after complex 1. With after complex 1, I mean that they can't pump protons and they give off their electrons to the same acceptor as complex 1, ubiquinol, which then becomes ubiquinol. And we're now going to the technical terms. So ubiquinol is the oxidized form and ubiquinol is the reduced form with 2 protons and 2 electrons. And there are even more complexes that come after complex 1. Now, I've sketched now our scene for what goes wrong if you just switch from one substrate to the other. Let's say you have glucose, then the amount of electrons that go in via complex 1 has a ratio of 5:1 compared to the ones that go in after complex 1, because you only use succinate dehydrogenase from the TCA cycle, and it's 5:1. But if you use fatty acid oxidation, especially if the fatty acids become longer and longer, then that is reduced to 2:1. So that's an enormous difference. Many more electrons coming in after complex 1. And now you can see that this could lead to a kind of traffic jam, especially if the cell hasn't time to adapt. You should go from one to the other, and you could get, that was what I hypothesized, reverse electron transport to complex 1 and ROS formation at complex 1. And now that ROS formation isn't just of a bacterium, it's a bacterium inside the other organism. So close to all kinds of molecules that could be damaged, etc., etc. Woo, that would be a problem. I think that peroxisomes evolved just because you have mitochondria inside the cell, mitochondrial vesicles are secreted into the environment. And this is the starting situation for part of the beta oxidation, because you don't need many enzymes for that, to go into another kind of organelle and reduce the amount of beta oxidation. So you get less internal ROS formation. And in that first article in 2011, I tried to sketch an evolutionary scenario in which small steps allowed that to come together in the peroxisomes with catalase, which is a normal enzyme that is made by archaea and other prokaryotes as well. So that could work. And we know from the analysis of peroxisomes that beta oxidation really is the oldest pathway in there. Now they do more, but that was the oldest pathway. And interestingly, in the meantime, we have now found that the enzymes that catalyze these steps in peroxisomes are the mitochondrial ones, except for the first one, which is different because now it can't give off its electrons to the respiratory chain anymore, but gives off its electrons to water forming hydrogen peroxide, which is then taken care of by catalase, which gives its name to peroxisomes, hydrogen peroxide formation. So that really should be different because it does something different. Mm-hmm. But the other three really are derived from the mitochondrium. And by the way, that was shown after I came up with the hypothesis, which is always a good thing. Mm-hmm. Something you predicted comes out. I'm getting over enthusiastic as you can. It's really okay. So peroxisomes seem to fit. Now I'm not going into an enormous amount of details, but if you look at, for instance, meiotic sacs, you could come up with a theory that this can be explained by internal ROS formation as well. Now I'm going to do that really quickly, and I hope that a lot of the listeners are going to come back with all kinds of arguments why this is bullshit, because that's the way science works. But if you look at meiotic sacs, then actually what you're looking at, you could say it's a kind of repair system, because it helps to get rid of mutations. And we know that a lot of the enzymes that are involved in the meiotic sacs come from archaeal pre-enzymes, you could say, that were involved in repair of DNA damage using recombination. So meiotic sacs really seems to have been selected because the amount of mutations went up. And there are people that say the only thing you need to explain meiotic sacs is Müller's ratchet. You know, of course, what this is.
No.
Müller's ratchet. Okay, so if you look at a gene and you look at a lengthy gene, there's always an amount of mutation occurring. Mm. And Müller's ratchet tells us that if we have an amount of mutations above a certain threshold, then slowly but steadily the information would disappear. In the long run, that would not be sustainable. Now, what are the two things that are important in Müller's ratchet? The frequency of mutation and the length of the message that you need for the complete organism. So a very complicated organism that and I'm not talking about junk DNA, but I'm talking about a real message that has a high mutation rate. Every new generation would contain too many mutations. So it wouldn't be possible to make a living. It would die out as soon as possible. Now, one of the things that you could use is meiotic sacs, because then you exchange parts and there will be in the new generation always an organism that would work. That's one of the reasons why people think meiotic sacs could be explained. Now, if you look at what happens during the merger, first of all, your genome becomes much bigger. Instead of the genes of one organism, you've got two organisms. So a doubling of the amount of genetic information. I'm of course saying that they have equal genome content, but that's not really necessary. There's more DNA that you have to protect. That we can agree on. And secondly, the mutation rate goes up because you have an internal ROS generator. So it's not, let's say, 1 in 100,000 nucleotides. It's now 100 in 100,000 nucleotides. So you have to come up with something that still allows the generation of a new generation that's not completely destroyed beforehand by Müller's ratchet. Now, if you want to look up these kind of arguments, you can find them in the PNAS paper that I wrote, in this case together with colleagues. So it's not the crazy person alone. There are a few other people that believe this. And I think it's a rather nice model to explain meiotic sex. Most models that try to explain it come up with things that indeed meiotic sex does, but that couldn't have explained why it evolved. And you can't say, well, the cell thought, you know what, I'm going to exchange parts because then there's going to be a bigger chance that I have a nice combination. No, there should be a driving force again.
Yeah.
Okay, so the other ones,
So we're still talking about single cells here, right? So
yeah,
I guess bacteria on itself deal with ROS by just throwing it outside, mostly.
yeah.
Why do single cells not just do that?
Okay, so first of all, the bacterium, part of the ROS formation could even be a mechanism to attack others or defend yourself. But as soon as the alpha proteobacterium ends up on the inside of another cell, then the host cell is confronted with internal ROS formation. And that's still a problem. And by the way, the spot at which ROS occurs in the respiratory chain differs. Complex 1 seems to go more inside of the alpha proteobacterium, the mitochondrion, while ROS formation at complex 3 indeed is a danger for the host because it's on the outside. So what's now called the intermembrane space. That, by the way, is a nice link to one of the other things. There's this enormous migration of mitochondrial genes to the nucleus.
Mm-hmm.
Hey, if you are close to a ROS generator, then it's better to put your genes behind the safe wall of the nucleus with much higher quality repair and polymerase that makes less mistakes, etc., etc. Another aspect that you see in eukaryotes that could be explained by internal ROS formation.
Yes.
So, and then all these antioxidant measures that I must admit bacteria and archaea already have, but really took off if you look at eukaryotes. Also ROS signaling, we now know that that's really important in eukaryotes. Quite a lot of things about differentiation and what a cell should do are signaled in the cell by ROS formation. Mm-hmm. So again, something where you think the nucleus itself. Why did the nucleus evolve? Well, if you have ROS generation inside something that was much smaller in the beginning, so it's really close also to the host DNA, well, membranes in between could really protect your maybe even chromosomes, layering of proteins over the DNA. ROS formation protection. You see, I'm going overboard. Practically everything, it's ROS, and mitochondria. So,
oh, that we're used to from you.
yeah, precisely. So, but actually, I think these are smaller steps, and you can imagine that this would lead to the eukaryote that we see today, not from an intrinsic tendency to become more complicated, but from things that that make biochemical sense. Mm-hmm. So that's why I'm so enthusiastic about symbiogenic theories. You see that I would end up at the final point where we started out in the discussion. So what do you think? Be very critical, but don't hurt my feelings. Yeah, I know. There's silence now. You're flabbergasted.
I like the theory of them evolving together more, but I'm not sure
about whether you can really explain everything from internal ROS formation. I get that.
Sure, yes.
Yeah. Oh, and I think this is a good point. So we all like symbiogenic theories, because the small steps and from the fact that they have to work together, and I have to be nuanced. There are a few things that I think really ROS formation, internal ROS formation, I should stress, was a major factor. But in other cases, you could imagine that it co-evolved with other kinds of evolutionary and selection pressures. I agree. So, but in the case of peroxisomes and maybe meiotic sex, these I really like. These could be explained mostly by looking at internal ROS formation. There are a few others, like that the cell became much bigger and that you have autophagy, etc. That where I think internal ROS formation contributed, but it's not the only selection force. And of course, if the cell becomes more and more complicated, other kinds of evolutionary pressures arise as well. So, but I like this runaway model of things coming up and creating new kinds of evolutionary pressures inside this from humble beginnings model, you could say. So that's but your critical note of but maybe you're trying to over explain things by just focusing on ROS. Yeah, I agree a bit. But hey, let's start out by trying to explain everything from this, and then slowly but steadily let's get more nuanced. But now let's go for the whole hog.
I also wonder if in this environment where you have both the pre-cell and the bacteria together, would you already also expect somewhat of adaptation to living with other cells? Because we're still talking about very single cell organisms here.
That's a very good point. First of all,
is that maybe also why they didn't deal with ROS to just throw it outside, because then you kill whatever else is next to you, basically?
Well, I know that if you look at alpha proteobacteria, and these are of course also later evolutionary examples. It's not the alpha proteobacterium that went into the symbiosis, or alpha proteobacterium-like organism that went into the symbiosis. But they had antioxidant measures, of course. They had to protect themselves as well. So it's not all antioxidant measures only came up after eukaryotic formation. Also, the archaeon had some antioxidant and could use certain cofactors that were dependent on oxygen, etc. I talked about the Asgard archaeon, that probably was the host. And the one that they cultivated needed a few other organisms. So these are really dependent on symbiosis.
Yeah.
And by the way, in that case, it's not an alpha proteobacterium. So a lot is still speculation. But you remember that I mentioned that this organism has these strange kind of extensions. That could have been already an adaptation that it uses to have this interaction with proteobacteria and other kinds of prokaryotes. We don't know whether other archaea were involved or other bacteria, but they seem to be part nowadays of rather complicated symbiosis in which not just two, but quite a lot of organisms work together to make the most of the environment. I think these kind of strange extensions that they showed with electron microscopy are adaptations for metabolite exchange. So indeed, precisely what you were aiming at when you came up with that question. Hey, didn't they already come up with some adaptations before integrating? Yeah, I think so. Yeah, and actually, that makes much more sense than these kind of models in which people say, we have a pre-eukaryote that phagocytoses, etc. And in this case, the adaptations were already taking place without the integration of one cell inside the other. So I think that's necessary.
I don't necessarily only mean with bacteria. I also mean like with cells that are like themselves. So the beginning of a multicellular organism, maybe.
There are clear examples of bacteria and archaea that already work together. Biological biofilms, for instance, in which bacteria and in a lot of cases, a lot of different organisms, but also there are situations in which we see that quorum sensing, that bacteria sense how many of them are present. Eukaryotes do this as well, but prokaryotes do that as well already. So you're right. There are, of course, a bacterium or an archaeon should know something about whether the environment is full of competitors, or you could also say collaborators. It depends on what they do. But yeah, there are sensing mechanisms for that. So, and these are also used for further adaptations during eukaryotic development. Yeah. So
I actually have a question along the lines of, so in this case, we're talking about one cell and one bacteria sort of going into symbiogenesis.
yeah.
But would the rate limiting aspect, so this is beneficial for both of them, obviously. Would the rate limiting sort of step for the cell be that it cannot take more of the bacteria up? Because that would be detrimental, because you would have much more ROS that it can't keep up with.
Okay. No, the interesting thing is that I describe it as simply as possible. So I talk about one archaeon and one bacterium. But of course, it's possible that there was uptake of many bacteria. We now have a mitochondrial network, but it can, from fusion and fission reactions, evolve into many mitochondria. And this could have been the begin state, that a few of them were taken up. There's no reason why it should have been just one. We are really in philosophical country here. We're speculating. We don't know. And we don't know, for instance, if there are people that come up with theories in which you have a syncytium of many of these archaea and many nuclei inside as an intermediate state. We don't know what happened. We only know that Leica, the last eukaryotic common ancestor, had peroxisomes, meiotic sacs, mitochondria, and was already like a real eukaryotic cell. But how did that arise from? We know that there are a few things we know for sure. That the host was an archaeon, and we know that the progenitor of the mitochondrion was an alpha proteobacterium-like organism. And that's the limit of what we know. And how that interaction occurred, one of them ended up inside the other. So that's another step we have to explain. But you can come up with syncytia, you can come up with very complicated symbiosis where many other organisms were involved. We really don't know. We know about Leica because we can reconstruct that much better than we used to, because we know many more eukaryotes that are highly unrelated. So we know that the diversification has been enormous. But now you can take trypanosomes, and you can take plants, and you can take dinoflagellates and plasmodium. And these are really unrelated. And what they all have in common, that is what Leica already had. And that's the only thing we know. And from Faeca, so that's the first eukaryotic common ancestor, a really completely hypothetical organism, to Leica, there's a lot of things we just speculate about.
It is surprising, though, that one organism outcompeted them.
Well, it could, if you talk about Leica, it could have been a population of Leica. So this is always difficult in reconstruction, but you can reconstruct this population to a large extent, and that outcompeted everything that went before in as far as other intermediate eukaryotic-like stages. Not, of course, the enormous diversification of bacteria and archaea. So but you're right. But that's the way it happened. Unless some people really still hope for this, we would suddenly identify a real intermediate. So not these derived states where we can show that they had a mitochondrion, like Giardia lamblia and Trichomonas vaginalis, all of these that don't have mitochondria but now have mitosomes or hydrogenosomes. Hey, this time I pronounced it. So maybe, and that would be an enormous breakthrough. But that would be a difficult moment for me if it doesn't have a mitochondrion, of course. If it really resembles a eukaryote, but really without a mitochondrion, that all my theories go out of the window.
Sad Dave.
That would be a sad day for Dave. Sad Dave. Yeah. So, but you never know. That's so. But that means that at least it is a real scientific theory. We predict certain things. So an intermediate like that would really show that, yeah, there was an intrinsic tendency for things to become more complicated, despite that there wasn't a pre-mitochondrion around. But I would bet against it. That's not too much money, of course.
A reasonable amount of
a reasonable amount of money. Yeah, that's it.
I still had a question regarding sort of you. At least I don't know if you actually said this, but that some of the symbiogenic cells with the probacteria, at a certain point you reach a derived state where they actually lost that mitochondria or that bacteria.
So you're talking about the Trichomonas examples?
I think so.
So, Jan, you still want to know a little bit about how that occurred?
Well, because this is the example where they would lose their mitochondria, right? So they had it at a certain point and then now just lose it. Would the environment that leads to that be something along the lines of there's no more oxygen, that they don't need it?
Oh, no, that's that we can... okay, there's still some debate about whether horizontal gene transfer can really explain all this, and I'm quite convinced that it can, but let's take a few examples here. So what happened? So let's, for instance, say, I'm not an expert, but you have an environment, for instance, inside the body of a large animal, where there are parts of the body that don't contain high amounts of oxygen because it's depleted by all the bacteria and all the other organisms using it up, etc., etc. And that means that there are still interesting environments where there is plenty of stuff that you could use because it's inside another animal, but there's no oxygen you could use. Now, there are many bacteria that can live very nicely in under anaerobic conditions. So not low in oxygen, but really no oxygen. Now, let's say that you have a eukaryote family that also lives inside these kind of animals. But hey, it still has a mitochondria and it still needs oxygen. You could imagine that, first of all, it needs not much oxygen because the respiratory chain has really high affinity for oxygen. If you look at cytochrome C oxidase, that can really scrounge up the lowest amounts of oxygen imaginable. That's so interesting if you do experiments, for instance, with isolated mitochondria. It really doesn't need much. It's still able to do that. But then let's say that it loses certain parts of the respiratory chain, and it still has cytochrome C oxidase, but it has an alternative complex 1, for instance, that straight away gives off its electrons to another intermediate. All of these kind of possibilities are there in eukaryotes. And then you can imagine that if it takes up just 1 or 2 genes via horizontal gene transfer, that it doesn't need cytochrome C oxidase anymore, and it starts using hydrogen as the final electron acceptor, and emits hydrogen. So I should say protons as the final electron acceptor, and this really happens in environments where a lot of the prokaryotes use these kind of systems. So if such a prokaryote dies, or if there's transduction by a virus, etc., this could end up in such a eukaryote. So that's what most people think happened with a few of these mitochondria that lost their mitochondria and, for instance, have hydrogenosomes. But also in the case of mitosomes, where they don't have a respiratory chain anymore, but just an empty sac that once used to be an active mitochondrion, a mitosome. These, of course, don't need oxygen anymore either because they don't have a respiratory chain anymore. So these kind of situations where you end up with something that was derived from a mitochondrion, but really does something completely different. Yeah, we have perfect examples. in some cases, we know that mitochondrial-like organelles are retained because the iron-sulfur clusters are still made for the rest of the cell. For instance, cytoplasmic ribosomal proteins need a iron-sulfur protein, and that is still made by the remnant of a mitochondrion. Because they are so intertwined, now we can't do anything anymore without mitochondrion. Do you hear this, dear listener? You can't do anything without your mitochondrion. So there
We
are
should put
all
that on a
kinds,
shirt.
there are all kinds of restraints here that don't allow just anything. But in the long run, there are now even eukaryotes that have lost that aspect as well and do this in a different way, taking up something else from horizontal gene transfer that allows them to do this function in the cytoplasm as well. So there are all kinds of these intermediate states, and they always happen in environments where these kind of genes could have been picked up from prokaryotes that already do it that way.
Okay.
Are you?
Yeah,
You're, okay. But there are still people that defend that these are old adaptations and that these hydrogenosomes weren't derived from lateral. Bill Martin, for instance, I think is still convinced that his original hydrogen hypothesis is true. And who am I to disagree with Bill? But I disagree. But he, of course, was enormously important because he came up with the first real symbiogenic model. And that was, as I said, a paradigm shift. So whatever happens, that was a major contribution. So even, dear listeners, even Suzanne looks totally unconvinced.
No.
Okay.
I think that's just
else?
my standard face.
This is what I podcast with.
Hey, I think we've been talking for quite a long time.
I have a final question.
Okay.
It's a little bit of an off-topic one, but you're of course the evolutionary expert. So
well, not expert. I love to dabble in evolution. I think it's wonderful.
We have talked about that 1 million years is quite a short time in evolutionary timelines,
yeah, it's
right?
a longer time for prokaryotes than for animals, of course. If you talk about our times of coming up with a new generation and you compare that,
Goes a bit faster.
That goes a bit, but still, 1 million years is not that much.
No. Well, I've this morning actually read an article that says that we're losing our little toe as humans because of evolution and also our wisdom teeth. Do you think it's actually possible to see evolution in humans?
Yeah, of course, we're animals. And that means that
but like in a lifetime?
Not in a lifetime. No. That could never happen. Because it's, now if people say that you can see it during your lifetime, then they don't understand how evolution works.
No.
Because the only change that can occur is due to mutations, and then you give something a little bit different to the next generation. But in a lifetime, that would mean Lamarckianism. So Lamarck had this theory of you change according to the things you feel during your life, you could say. So a giraffe would get a longer neck because it has been trying to get to these top branches and it doesn't get there. And during its life, it changes. But that's not the way evolution works.
But how long do you think it would take to lose our tiny toe?
Depends on the pressure.
Well, it's not. First of all, if we talk about Darwinian evolution and Darwinian evolutionary change, then you should first of all remember, yes, selection is a really strong force, but also there are neutral processes. A lot of it's just dumb luck. And bottlenecks, etc. It's not all about perfect adaptation. So there are these two forces, chance and necessity, as Monod used to say. And the necessity is now that you really have selective forces. And chance is that, let's suppose that one of the three of us, you two, because then we at least have new generations. So, but you go to an island and the rest of humanity is destroyed. Yeah, these things happen. But you are spared this terrible fate and the complete future of humanity comes out of you two. Well, you have certain very specific things that most people don't have. And then afterwards we reconstruct and we say, yeah, that's of course evolution. No, it was sheer chance that Jaron had an enormous amount of hair flowing. I'm really jealous, dear listener, because I'm bald. And now we get humanity that's much more hairy than we are at the moment. And that was due to chance because of the island effect that you were. Okay, so it's chance and necessity. But let's say that you want an answer. So how quickly would that go? Well, the wisdom teeth, I'm not quite sure. If we still have civilization and we don't need to chew very hard with these kind of, it's probably not unthinkable that they would disappear in about 200 generations. I'm spitballing here, that's clear. And the small toe, I really love my small toe. Why should it disappear? But clearly that sometimes it goes faster. But the only way that we can look at that is if we have very good and well-preserved fossils, for instance, of humanoids, and then we can check for certain tendencies.
Yeah, I thought the article was a bit weird because we don't have half of a population missing their tiny toe, for
That
example.
you know of.
So
yeah, precisely. You can't look inside
I think
the shoe.
the beginning of evolution to see that's impossible to see.
Yeah. You can sometimes predict a little bit, like what I just did.
With the wisdom
teeth.
Yeah.
So.
But at the same time, there's no pressure to.
Precisely. It doesn't have to happen. No.
Because we all remove them and we're fine.
No, the interesting thing is that people always say, yeah, you can predict because there's more complexity. So the tendency was that we got bigger and bigger brains. And then people, they when they draw the humanoid of the future, it has got an even larger brain and a smaller body. Who knows? There are people that say, no, actually that bigger brain was due to sexual selection. And of course, yeah, now it works out nicely and it gives us but it's just dependent on the fact that women, when they chose, they have a large influence on sexual selection. It's not only how males fight amongst each other, and it's also women that say, no, you might have one, but I still prefer the other one, and maybe it took very intelligent women to choose between men, and one of the things they liked was intelligence, not sheer force. So there are people who think that this led to this. This, by the way, is an example of a very rapid process, much too rapid for normal evolutionary forces. It really, in practically no time, a few million years, that brain became so big that it now leads to all kinds of problems for women during birth. What?
Still a couple million years.
Yeah, but still. But you can't predict that. There are also people that say, yeah, we'll become dumber and dumber because now artificial intelligence will do and we'll have tiny brains. It's a fool's game. You don't know how it will work.
I think it's very difficult to see evolution happening except for when you're already quite far into it.
Precisely. And the interesting thing is, people sometimes say, yeah, but you can't prove it because you can't see it. Yes, we can, but we have to look at prokaryotes or very simple eukaryotes. So there are these nice cultivations of bacterial cells where they keep on just recreating new ones time after time in the laboratory. And there's this very long culture of bacteria, E. coli, for instance. And they can reconstruct that due to chance. Certain things occurred that changed these bacteria. And then you can really see evolution at work. And it's again chance and necessity, just as we talked about. So the only thing that you can say is also for animals such as ourselves, chance and necessity will work in the future, but that's not enough to predict the evolutionary future of mankind. And there's another thing which is really important, and that for us as human beings, cultural evolution at the moment is much more important than Darwinian evolution. And our culture and the things that we make and the things that influence us and that we are filled up with from birth in our brain, that goes with an enormous speed. Cultural evolution, that goes during lifetimes. Biological evolution doesn't.
No.
And actually, that's really exciting. So a Greek person from 400 years BC was completely the same, biologically speaking, as us, but he wouldn't understand a lot of things that we talk about and that we understand because of cultural evolution. So that's much faster than
That's your
talking
other
about
hobby.
the little toe and about the wisdom teeth.
I don't think we have to worry about it.
No, I don't think so.
Okay.
Nothing else?
No.
So did we explain everything, dear listener? I don't think so. But it was fun.
Yes.
Don't you think so?
It was fun to have you again.
Yes.
Thank you so much for doing this again.
Hey, I kept on talking. It was my pleasure.
Well, if you have any questions, suggestions, comments, or reasons why this is absolutely not true, of course, you can reach us via our website, thestrugglingscientist.com, or via our email address, thestrugglingscientist@hotmail.com. Definitely also check out our amazing t-shirts on the website, and check out our social medias. Jaron, which ones are those again?
Twitter, Instagram, Facebook, LinkedIn, and Pinterest.
Yes, all of them, I think.
Yes.
We don't do TikTok.
We do not do TikTok. No.
Okay.
That's where we draw the line.
Well, thank you all for listening.
Wait, we also please leave us a review on Spotify and Apple iTunes, Apple Podcasts.
Apple Podcasts and Spotify, indeed.
Yes.
Thank you all for listening. Bye.
Bye.
Bye.